Chapter 1.4, Continuity and One-Sided Limits, Day 2. One-sided limits with piecewise and step functions. A one-sided limit is when you just look at what a function is approaching from one side. The symbolism for that, if you're looking at a left-hand limit, we're going to say the limit of f of x as x approaches c. We put the little negative up there to show we're coming from the negative side. And what that looks like, if I'm looking to find the limit of this parabola at this point, and I'm looking for just the left-sided limit, I'm going to take from the left side of the graph and come and get closer and closer to it. So right there, that's the left-hand limit. The right-hand limit is going to come from the positive side, meaning I'm taking my right hand, which is in the positive numbers, and I'm going to approach the limit from the right side. And you can see in this case, the left hand and the right-hand limit agree, meaning they approach the same number. If the left-hand limit exists and the right-hand limit exists and they're both the same, we say the limit exists. One-sided limits very nicely describe the behavior at the end of radicals. If you remember what the square root of x looks like, you've got a graph that starts here and goes off. Well, you can see the function exists at 0 and is defined at 0, but the limit doesn't. Well, we can see that from the right it approaches 0. So this allows us to kind of say and evaluate what's happening there at the right-hand side at 0. A new function, the step function. This is called also the greatest integer function, meaning y equals the step function of x is the greatest integer less than or equal to the number. Some examples. The step function, or the greatest integer of 2.7, is 2. Okay? The greatest integer less than or equal to 2.7 is 2. The greatest integer of 4.987 is 4. Pretty simple for positive numbers. For negative numbers, you need to stop and think a little bit better, because they're a little bit backwards. The step function of negative 2.5, the greatest integer less than or equal to negative 2.5. Since we're in the negatives, when you go less than negative 2.5, the answer is negative 3. And obviously, if you have a step function of an integer, what's the greatest integer less than or equal to 7? Well, that's 7. Okay, graphically, this is what the step function looks like. The greatest integer of 3.5 is 3. Greatest integer of 3.7 is 3. And it ends up looking like a step function. So you can see with the step functions, there is discontinuities at every integer in the left and the right-hand limits disagree. So if we look at some examples of some limits of step functions, the limit of the step function of x as x approaches 7 from the positive side. So if we look at 7 on this graph, 1, 2, 3, 4, 5, 6, 7, it would be your 6, 7 would be a little bit higher. You can see it would be at 7. If you look at 1 from the positive side, we approach 1. 2 from the positive side, we approach 2. So the limit, the step function as x approaches 7 from the positive side, is 7, because we always round it down to that 7. Okay? The limit as x approaches 4 from the negative side, like normal limits, the first thing you should try is plug and chug. So if I plug 4 in here, I get 0 over 0. And what do you do for radicals? Well, you need to multiply by the conjugate. You need to rationalize it. So multiply top and bottom by the square root of x plus 2. All right. So the limit as x approaches 4 from the negative side. The top will simplify to x minus 4. The bottom will leave alone. And we got x minus 4 canceling on top and on the bottom. We're left with 1 over, and if we plug in 4, square root of 4 is 2 plus 2 is 4. So if the limit is 1/4, that means the left and the right hand limit's got to be the same. So the left hand limit would also be 1/4. Okay, let's look at this one graphically. You should be getting some idea of what's happened graphically on this one because we've done it a couple times now, but we'll do it one more time. Do the absolute value, math, over to number, absolute value of x minus 2. Divided by x minus 2. See, it's 2 straight lines. We've got to jump at 2. What's happening for this limit? Well, the limit from the left of our function, the limit from the left, as we come to the left, we're getting closer and closer to -1. And the limit from the right, we get closer and closer. This time it's 1. The left and the right disagree, so our limit over all does not exist. All right? So now when you evaluate limits, you want to start looking at left and right hand behavior. And this is the symbolism for left and right hand behavior. Here's a step function, or a piecewise function, meaning it's coming in 2 pieces. So we want to evaluate the limit of f of x as x approaches 2. We want to first look at it from the left. The limit of f of x as x approaches 2 from the left, the negative side. Well, this is the negative side. So I'm going to plug 2 into there, and you don't need to show this step. You can do this mentally. 2 squared is 2 is 4. 4 times 2 is 8. 4 minus 8 is -4 plus 6 is 2. All right, let's approach from the right. The limit as x approaches 2 from the positive side. This is the positive side here because it's the numbers greater than 2. So if we stick 2 into that piece of our piecewise, 2 squared is 4. We got -4. 4 times 2 is 8. -4 plus 8 is 4. 4 minus 2 is 2. The left-hand limit and the right-hand limit are both 2, so the overall limit is 2. Left and the right agree. And another piecewise function. Find the limit as x approaches 1 of f of x. Well, evaluate it from the left. All right, do the left right here. If we plug 1 into that, we get 1. Let's evaluate it from the right. Limit as x approaches 1 from the positive side. Okay, this is the right. If I plug 1 to there, 1 minus 1 is 0. The left and the right do not agree, so our overall limit does not exist. Okay. So in conclusion, the left-hand limit and the right-hand limit You're just breaking your overall limit into two sides. As long as those two sides exist and agree, you have a limit for the function.